In 2015, psychologist Arthur Aaron set up a simple experiment that unexpectedly went viral online. Two complete strangers sat in a quiet room just a couple of meters apart and did nothing. No talking, no phones, no instructions beyond one. Look into each other's eyes for 4 straight minutes. If you've seen the clips, you remember the reactions. Fidgeting at first, nervous laughter, glances away. Then something shifts. The stranger's breathing syncs up. Some people start crying. Others say they feel weirdly close, almost like family. When the researchers finally say stop, many of them don't want to break eye contact. That emotional punch came from a surprisingly simple visual cue. The way humans can track exactly where another person is looking, almost instantly. Your attention wasn't on their nose or their eyebrows. It was locked on the bright white area around the dark center of the eye. Most people assume this is just what eyes look like. But the result is surprising enough to make headlines in biology textbooks too. Because almost no other mammal on Earth has this kind of visible eye white, the sclera, that humans do. Not chimpanzees, not gorillas, not wolves. So how did this odd, exposed, and frankly vulnerable feature evolve in our species, and not in our closest relatives? To find out, we need to leave the psychology lab and go back almost 2 million years, to the first hominins who looked where someone else was looking. Take a second to picture a chimpanzee's face. Dark skin around a darker eye, with just a hint of lighter tissue if the light hits at the right angle. Now imagine pausing on a close-up of your own eyes, a dark iris, sharply outlined by a big, pale background. Biologists call that pale area the sclera. Technically, most vertebrates have one, but in almost all mammals, it's camouflaged, pigmented, shadowed, or buried behind eyelids and fur. In humans, it's large, bright, and highly exposed. Here's the myth most of us carry without noticing, that this is just the normal mammal setup. It isn't. A 2017 comparative study of primate eyes found that humans rank at the extreme end for sclera brightness and symmetry, while our closest relatives, like chimpanzees and bonobos, usually show darkened, patchy, or partially hidden whites. This stark contrast between iris and sclera makes it easy to see not just whether someone's eyes are open, but exactly where they're pointing. Even a tiny sideways glance is obvious. Why does that matter? Because gaze is a shortcut to someone else's mind. Following where another individual is looking tells you what they've noticed, what they're interested in, and maybe what they're about to do. Quick reminder, this is still a relatively small channel, and a simple like or subscribe genuinely helps us keep making deep dives like this. If visible eye whites are so useful for reading attention, why didn't evolution give them to every social animal? Hundreds of millions of years before any hominin walked upright, eyes were already locked in an evolutionary arms race. Trilobite fossils from the Cambrian, around 520 million years ago, show complex compound eyes that could detect motion and contrast in murky seas. Vision helped animals find food and avoid becoming food. But at this early stage, the eye's job was mostly about light and dark, predator and prey. Where you were looking did not need to be obvious to anyone else. In fact, it was probably safer if it wasn't. Fast forward to the first primates, appearing at least 55 million years ago. Fossils like Tailhardina asiatica from China, described in 2002, already have forward-facing eye sockets. This gave better depth perception for leaping through branches, but still didn't advertise gaze direction. As primates diversified, many lineages developed bare skin around the eyes, or striking facial patterns. Think of ring-tailed lemurs or colobus monkeys. These markings probably helped individuals recognize each other in dense forests. Yet even in these early primates, the sclera remained relatively hidden or pigmented. The eyes signaled arousal or aggression by widening or narrowing, not by clearly telegraphing where attention landed. So something had to change later, specifically in the hominin lineage. Somewhere between dark, secretive primate eyes and the open, readable eyes of modern humans, a new social pressure appeared. To find that pressure, we need to step into the world of early Homo, where cooperation started to matter as much as competition. Around 1.8 million years ago, fossils like KNM ER 3733 from Kubifora in Kenya show us Homo erectus with a modernish skull shape and expanded brain case. These hominins hunted large game, used more sophisticated stone tools, like the Acheulean hand axe, and likely shared food at central places. Picture a small group on the savannah, scanning for gazelles, and more importantly, for lions. If one individual spots movement at the edge of the grass, the fastest way to alert others isn't sound, which could also alert predators, but gaze. A sharp turn of the head, a fixed stare. Experiments with modern apes show an important contrast here. Chimpanzees can follow head direction, but they're much worse at using just eye direction, especially in subtle situations. Human infants, on the other hand, reliably track eye gaze by around 6 to 9 months old, even when the head stays still. Here's the irony of evolution. What makes us vulnerable can also become an advantage. Making our eyes more conspicuous might have risked revealing our focus to competitors. But in tight-knit groups that depend on cooperation, the benefits of instantly sharing attention may have outweighed that cost. Selection could then favor individuals whose eyes made their gaze a little easier to read, perhaps a slightly larger opening, a slightly paler sclera. Small differences, compounding over hundreds of thousands of years. But cooperation alone doesn't explain why our sclera is so unusually bright. In 2002, cognitive scientist Michael Tomasello and colleagues proposed what's now called the Cooperative Eye Hypothesis. The idea is deceptively simple. Human eyes evolved to be high contrast, with a white sclera and darker iris, specifically to make gaze direction easier to perceive. Because our ancestors relied heavily on shared attention. Think of joint tasks: building a shelter, butchering a carcass, tracking an animal. If you and I can coordinate silently just by noticing where the other is looking, we waste less time, avoid accidents, and hunt more effectively. Studies comparing humans and great apes support this pattern. Even in nonverbal experiments, human adults and toddlers use eye gaze to guide cooperation far more flexibly than chimpanzees do. We point with our eyes. We reassure with our eyes. We even argue with our eyes. Myth-busting moment. It's common to assume language did all the heavy lifting for human cooperation, but gaze and gesture likely laid the groundwork long before fully complex speech existed. Making gaze legible might have rewired how our ancestors understood each other's minds. Not just, is that individual looking at me, but what exactly are they interested in? What will they do next? Still, the cooperative eye hypothesis mainly addresses function. It doesn't fully answer why the sclera had to become so bright, or why it stayed that way, instead of reverting to a more camouflaged state. Now, we step into the part of the story that can feel uncomfortably personal. Sexual selection doesn't just shape peacock tails and deer antlers, it also shapes faces, including eyes. Human sclera are not just bright, they're also unusually uniform in color. When we're healthy and young, they tend to be clear, smooth, and evenly white. With age or illness, they often become yellowed, reddened, or blotchy. That makes them an honest signal of condition, hard to fake, easy to inspect. Picture a small hunter-gatherer band tens of thousands of years ago. Courtship isn't a candlelit dinner. It's a lifetime commitment to share scarce food and raise helpless offspring. Choosing a partner with clear, symmetrical eyes could be an unconscious shortcut to picking someone with good health and lower infection risk. This is where sexual selection could amplify a trait first nudged by cooperation. Once gaze readability is moderately useful, preferences for eyes that are even more striking and easy to read can kick in. Individuals drawn to clearer sclera choose mates who pass on both the trait and the preference. Some researchers have suggested that the pattern of human eye morphology, big visible sclera, rounded eye shape, hairless surrounding skin, might be part of the broader self-domestication trend. Like domesticated animals, humans show suites of traits linked to reduced aggression and increased social tolerance. In that framework, visible eye whites become both a social tool and a cosmetic cue. Look closely at photos of people from around the world, and you'll notice subtle but real variation in eye appearance. Some populations have slightly darker sclera on average. Some show more visible blood vessels, and eyelid and epicanthic fold shapes vary widely. This next part is the one that unsettles people most, because eye color and eye shape have been misused in racist ideologies for more than a century. So it's important to be precise. Genetic studies indicate that the basic pattern of a bright, depigmented sclera is shared across all modern human populations. There is no group that lacks visible eye whites in the way other primates do. Differences we notice are about degree, not presence or absence. For example, variation in iris color across Eurasia, blue, green, hazel, is tied to mutations in genes like OCA2 and HERC2 over the last 6 to 10,000 years. These changes affect the iris, not the sclera, though they can make the contrast look even more intense. Anthropologists studying skulls from sites like Sungir in Russia, about 34,000 years old, or Tafaralt in Morocco, around 15,000 years old, can't directly see soft tissues like sclera. But the overall orbital morphology suggests that our distinctive eye region is an ancient, species-wide feature of Homo sapiens. So visible eye whites are not a marker of race in any biological sense. They're part of the shared toolkit our species uses for communication. Neanderthals, our closest extinct relatives, lived across Europe and Western Asia from at least 400,000 years ago until around 40,000 years ago. Fossils like the La Farasiwan skull in France and the Shanidar remains in Iraq give us detailed views of their faces. Neanderthals had large eye sockets, sometimes even bigger than those of modern humans living at similar latitudes. Some researchers argue that these large orbits reflect adaptations for low-light environments, like Ice Age Europe's long winters. But what about sclera? Bone can't preserve soft tissue pigmentation, so we can't directly see whether Neanderthals had bright eye whites. However, comparative anatomy suggests their basic eye layout, forward-facing, exposed, ringed by bare skin, wasn't radically different. A 2020 analysis of digital reconstructions of Neanderthal and Homo sapiens faces found overlapping ranges in eye shape. That implies that bright, visible sclera may have already been present in the last common ancestor of both lineages over 600,000 years ago. Perhaps in Homo heidelbergensis specimens like those from Cima de los Huesos in Spain. If that's correct, it means that conspicuous eye whites weren't a brand new feature of our species, but part of a deeper hominin pattern of intensive social communication. And Neanderthals weren't the only cousins in this story. Genetic traces from Denisovans, identified from a finger bone and teeth in Denisova Cave in Siberia, hint at another hominin with whom we interbred. Neuroscientists have spent decades mapping how our brains respond to eyes. Functional MRI studies show that a region in the temporal lobe, the superior temporal sulcus, lights up specifically when we see shifts in gaze. Another area, the amygdala, responds strongly to eye contact and expressions of fear or anger. Here's the mechanism, humanized. Imagine a child in a prehistoric camp. They look up and see an adult suddenly freeze, eyes widened and fixed toward the bushes. Before any words, before any pointing, the child's attention yanked in the same direction. That instant transfer of focus could mean the difference between safety and a leopard attack. Experiments with modern adults show that even when we're told to ignore someone's eyes, our attention reflexively jumps to whatever they're looking at. This happens so quickly that it suggests a deeply wired system, sculpted by many generations of selection. There's another twist. We don't just follow gaze, we infer intentions from it. If someone's eyes flick toward an object and back to us, we treat that as a silent invitation. If they maintain a stare at us, we read dominance, interest, or threat, depending on context. Our visible sclera supercharge these inferences. They act like high-contrast arrows that our brains are primed to decode. All of this brings us back to that first experiment with 4 minutes of eye contact. Return to that quiet room in 2015, where two strangers are still sitting in front of each other, trying not to laugh, trying not to look away. Under the fluorescent lights, their sclera look almost too bright, like little moons around dark pupils. At first, the exercise feels awkward because our everyday lives rarely hold eye contact for that long. But part of why it becomes powerful is exactly what we've traced through prehistory. Our eyes are built to be readable. Those white backgrounds are the result of millions of years of incremental changes. From early primates leaping through Eocene forests, to Homo erectus scanning the East African savannas, to Neanderthals under Ice Age skies, hominins that could quickly share attention and intentions gained an advantage. Cooperation pushed our eyes to become clearer signals. Sexual selection polished them into condition indicators, favoring youth, health, and subtle symmetry. Social living tuned our brains to treat the slightest flicker of gaze as rich data about someone else's mind. The quotable version might be this: our eyes didn't just evolve to see the world, they evolved so the world could see us. Most other animals keep their attention partially hidden. In many species, not knowing exactly where another individual is looking can be useful. It protects private intentions, masks fear, conceals interest in food or mates. Humans made a different bargain. We traded some visual privacy for deeper mutual transparency. In small bands where your survival depends on others accurately reading your needs, your fears, and your focus, that trade seems to have paid off. But there's a cost. When your eyes are so exposed, lying becomes harder. People notice the microglances, the avoidance, the little mismatches between what you say and where you look. That may be one reason we invented cultural rules about when it's polite to meet someone's gaze, when to turn away, and how long is too long. So the next time you lock eyes with someone on a crowded train, or hold a friend's gaze a moment longer than usual, you're acting out an ancient negotiation between privacy and connection, between secrecy and trust. Our visible eye whites are a reminder that as a species, we doubled down on being legible to each other. We're the primate that wears its attention on its face. What do you think this says about us? If you could redesign the human eye, would you make our gaze more hidden or even more readable? Let us know in the comments. And if you enjoyed this journey through our evolutionary gaze, consider subscribing so we can keep exploring how the past shaped the most ordinary parts of being human.